So for this interactive video, we're going to be talking about the complex zeros or complex numbers in general. So if you notice, we're actually on chapter 1.6. We're on unit 3, but we backtrack all the way to chapter 1 because I originally did not have this in chapter 1 because it aligns more in unit 3 than it does in unit 1. So we're going to take the real number system and we're going to expand it to something called the complex numbers. What I mean by that is that we're going to have a system that has all the real numbers and more. So before we talk about the complex number and I define it to you guys formally, we got to define this symbol I. This is a symbol, by the way. This is called the imaginary number in particular. Your book gives the definition I is equal to square root of negative 1. What's more powerful for this section to use is I squared equals negative 1. This is the one that I would prefer you guys to accept for now at the very least. And there is a big difference between these two definitions. If you think about it, if you understand how to solve for I here, you would have to do the plus or minus square root. In this case, the square root is assumed to be positive for the outside. And this definition in particular says that, hey, we can't square root a negative number, and we cannot. We don't have anything that, I guess, satisfy that condition. So mathematicians created this symbol so it can be constructed. All right. So because there's going to be a lot of wordings and everything, I'm just going to make this simple. I'm going to say I have a complex number, z. All right, that's the name of the complex number, z. Now, z is a complex number in the form of a plus bi. B times your imaginary component, pretty much. Where a is the real component, a is a real number, and b is the imaginary component. B is a real number. But this is the confusing part that students have. Even though b is a real number, the entire thing is the imaginary component. Okay? So let me give you an example real quick. These are examples of complex numbers. 3 minus 2i. This is a real number. This is a real number. This is the real component. This is the imaginary component. Boom. So let me zoom out so you guys can see that. Boom. Let's take this example, 4i. In particular, your real component is 0, but your imaginary component is 4. In this case, your real component is 9. You have 0 as your imaginary component. And then over here, we have your real component is 0. Pi is still a real number, even though it's an irrational number. So b is equal to pi. That's your imaginary component. All right? We need to separate these complex numbers with real components and imaginary components. So, and if you think of it this way, a real number, the number 9, is a complex number as well. It is a complex number. So essentially, it's all the real numbers and more. It has imaginary components. So this is an example of the complex plane. If I give this as a rectangle, the real numbers is a piece of the complex plane in particular. Now that we're working with a newer system, we need to talk about operations on these numbers because it's not as intuitive. Now, thankfully, there are connections that we have to bridge the gap. So let's talk about addition and subtraction. To add or to subtract complex numbers, you want to treat the components as terms in a sense. So all you have to do is add or subtract like terms. That's it. All right, let's take this example. The first complex number is z1. Let's call that z1, and it's 2 minus 4i. Let's call the second complex number z2, where it's negative 5 plus I. Let's say I want to add them together. Well, if I wanted to add them together, I'm just going to use parentheses. This is a complex number 1, complex number 2. This should be z2, by the way. I apologize for that. But complex number 1, complex number 2. Let me go fix that. All right. All I'm going to do is add the real components with the real components and the imaginary components with the imaginary components because those are the like terms. So 2 plus negative 5. That's my real component. Negative 4i plus I is my imaginary component. So I'm going to do that. And when you add things, you just add the coefficients. So it works the same way as like terms in a sense. All right, and when you do this, you get negative 3 minus 3i, which is that's the new complex number. That's the summation of z1 and z2. All right, now, how do we multiply then? Multiply, Multiplying, thankfully, there's something that we have done that's similar to multiplying. So here's the definition of multiplication. It says that if z1 is equal to a plus bi, z2 is equal to c plus di, this is what it's supposed to be calculated as. But don't worry, this is the exact same thing as foiling. It works the same manner, all right? So you can FOIL this out to actually calculate that. If I FOIL this out, boom, 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 I have 4 times 1 is 4, 4 times 3i, 12i, negative 2y times 1, that's negative 2y, and negative 2y times positive 3i, which is negative 6i squared, right? You remember I times I is I squared in particular. Now you have all of these terms in particular. You need to simplify this. So notice that I squared, the definition I gave you guys, is equal to negative 1. So let's just replace this entire guy with negative 1. Then I have 4 plus 12i minus 2y, and this is negative 6. The negative belongs to the 6. Negative 6 times negative 1, which is positive 6. Boom. So you see here, this was an imaginary number, or imaginary component, and it turned into a real number because I squared it. That's a very important rule. So then I can combine like terms. 4 plus 6 is 10. Negative 12i plus negative 2i is negative 10i. It should be positive 10i, I apologize. Right, just combine like terms. Now, again, I want you to observe that the last term is constant. That's a very important role, all right? So now, we need to go with this definition if I want to talk about division. If z equals a plus bi is the complex number, we say that z bar, which is equal to a minus bi, we call that the complex conjugate. So it's going to be the negative of your imaginary component. That's your complex conjugate. And why is this important? Why is it important to have a complex number and know its conjugate? Well, we'll see why is when we divide. So let's take this example for division. The definition in your book for division is this. If I have a plus bi divided by c plus di, two complex number, I can write this as a fraction because that's what division actually is. But the definition the book gives you is this. This is hard to memorize. It's a lot. I can't even memorize that. All right? So instead, we use the idea of complex conjugates to calculate this definition or to arrive to this definition. So let's take 4 minus 2y divided by 3i. If I want to divide this out, I'm going to multiply this entire fraction by negative 3i over negative 3i because that's the complex conjugate. All right, I multiply by the complex conjugate of the denominator. And then what's going to happen is that when we calculate this out, multiply them out, your denominator, negative 9i squared, turns into a real number, or only a real number. Boom. So that's very nice. You don't get a imaginary component in my denominator at all anymore. Boom, boom. You can calculate this out. I replace I squared with negative 1. Then I get all of this. And then I have, I rearrange the term. I put negative 6 first. So negative 6 divided by 9 first. Then I did 12i divided by 9 over here. Okay? Just in case you guys were confused. And I want to separate my real component with my imaginary component every single time. That helps me understand what my number looks like. So let's take this example. 3 plus 5i divided by 1 minus 2y. Well, I'm going to turn this into a fraction because that's what division is. And I'm going to multiply by the denominator's complex conjugate. 1 minus 2y, the conjugate is 1 plus 2y over 1 plus 2y. Now, I do this because technically a number divided by itself is 1. So I'm not changing the value of my problem at all. I'm just multiplying by 1. It's just going to change its representation. So if I do so, I have to FOIL this out. FOIL the numerator with the numerator and FOIL the denominator with the denominator. If I do so, I get this entire mess right here. I squared is equal to negative 1. I'm going to replace all the I squared with negative 1 here, and I'm going to multiply them out. Positive 10 times negative 1 is minus 10. Negative 4 times negative 1 is positive 4. And then I combine like terms. And then I have negative 7 plus 11i over 5. Again, the denominator is going to turn into a real number if you multiply by the complex conjugate. And now I can separate my real component with my imaginary component. Negative 7 over 5 plus 11 over 5i. Okay? That is very helpful to know how to do division instead of memorizing that formula in particular. Now, it's important you know that when I have a square root of a negative value, I can always factor out a negative 1 to that number and then break up the square roots. So I have square root of negative 1 times square root of 9, which is exactly I times 3. This is not plus or minus because the square root is assumed to be positive. Okay, so I get 3i here. However, if I have x squared equals negative 9 and I wanted to solve for x, I have to apply the plus or minus square root. This right here, I didn't apply the square root. It's already given to me that is positive. But over here, I applied it to solve for my equation. And that's why I have two solutions in particular, plus or minus 3i. So be wary of that. I will see you guys next time on 3.5. Take care.